Okay, for those who don't know how to deal with the example 2.2, here we go. So example 2.2. Actually, this problem is not that difficult, okay, but you need to combine what we learned from topic 1 and 2 to solve the problem, okay. So as I mentioned, part A should be straightforward, okay. So we just need to apply one of the equation. So this equation comes from turn on and turn off characteristics. I hope that you still remember. Okay, and then all the parameters are given. Okay, so we just need to substitute all the parameters in, and this one, is the time intervals, and then switching frequency is given. Right? Oh no, sorry. The switching interval is given. So here we need to do the reciprocal. Yeah, of switching interval. And so at the end, we'll have this value. Okay, 3.6 watts. Okay, and then part B. Oh no, not part B. Conduction loss. So conduction loss by R, right? So R is given, and then I naught square. So this one comes from the basic definition of the root mean square value, okay, of pulse string waveform. Okay, and this one is given 20 milliohm, and D is unknown. Okay, but I just showed you that we can find the equation to calculate the duty ratio in topic 1. Okay, so actually here we have the duty ratio is equal to the ratio of turn on interval, and switching interval. Okay, and then according to the topology of the buck DC-DC converter, so it can be like this. And both parameters are given in the problem, so we can just substitute the parameters in. Okay, I know is also given. Okay, so we can get this value. Right? Okay, part B is also quite straightforward. We can apply one of the equations. So here is for the dial forward. So again, we here can recall our memory. Okay, so it is actually the conduction loss of the dial, right? So in that topology, if you want the dial conducting, so the period of time should only be 1 minus d. Okay, so 1 minus d, and then Vi. So this is the forward potential, and then I naught. Substitute all the parameters in. So here we just calculate. Okay, so we can do like this. Substitute the parameters in. Okay, it's equal to 2.1 watts. Okay. Part C, if you don't remember the definition of the efficiency, okay, so you can refer back to one of the slides in topic 1. Okay, so but actually for this one, I think it's quite I cannot say easy, okay, but we can recall like this, right? So do you still remember this one? This is in, this is out, and this is loss, right? Okay, so P in is equal to P naught plus P loss. And then the definition here is the ratio of P naught and P in, right? Okay, so it means that from this block diagram, so here should be P naught plus P loss. Okay, so actually we don't need to remember or memorize. We don't need to memorize the equations directly. Okay, so we can recall our memory using this kind of picture. Okay, okay, and then P naught is equal to V naught I naught. So here also V naught I naught, and then plus. According to the problem, we just need to take into account of 3 power losses calculated in task A and B. So here we just need to write down 3 types of power losses and then put it down. Okay, and actually we now have all the parameters. Okay, so just need to substitute all the parameters in. Okay, and at the end we will have about 95%. Okay, so that is the solution. It's not very complicated, right? But as I mentioned, we need to refer the knowledge that we learned before. So actually, there's also the development of the subject. Okay, so don't underestimate even the simple parts. Okay, okay, and here I also have some messages that I want to deliver to you. Okay, so even though you can use your calculator, right? But you still need to write down those parameters. Okay, so don't ignore the order of magnitude. They are very important. So sometimes there is a nano, so 10 to the minus of minus 9, okay, and sometimes micro, so 10 to the power of minus 6, even sometimes mini, okay, so please later can hey, okay, yeah, and so please pay attention on the order of magnitude, otherwise you should have you should get the wrong answer, okay. And then the second message that I want to deliver you, okay, so uh, in case the test or exam is closed book, please leave me at least the equation. Okay, if you don't know how to find out those parameters, okay, I will give you a mark. That's just for me, okay, not for Yang. Yang will have his own style, okay. So if the test or exam is closed book, please at least give me this equation, okay. So if you it will give you at least 1 mark, okay. So and then substitute the parameters and then the final answer. In my opinion, 1, 2, 3, 3 steps are also very important. Okay, this is because sometimes you may not write down the correct parameters here, and then this equation can give you a mark. Okay, and it's also very important to list all the parameters in the equation. It is because sometimes the final answer may be wrong. Okay, so with the good practice, I think it's better to list or write down the original equation and then the equation with the parameters and the final answer. Okay, yeah, that's the message that I want to give you. And for the given A, the D in part A is not equal to that's different. Okay, so your question actually raised a very good um, conceptual issue. Okay, so actually from the question in Hey uh, question, okay, so he said that why uh, let me interpret this. So T on, right? T on, why we don't do like this, right? Why we don't do like this? Why? Actually, this should be wrong. It is because the first thing we need to look at the order of magnitude. 30 nanosecond, 20 nanosecond. This should be much shorter than this one, right? Microsecond. Okay. Uh, so here from the parameters, we know that we should not be able to do this. Okay. And conceptually, uh, this one is the switching on interval, and this one is the switching interval. So we can think like this. So here is the switching on, switching, and here is on interval. It's different, right? So here may be the turning on time, and uh, this definition should not be the same as the on interval. Okay, so this on interval is after switching steady uh, the period of time when the MOSFET is on. Okay, and here much shorter the nanosecond, so it is the switching on or off interval. Okay, so we cannot do like this. Okay, so is that okay, Jin Hei? So any further question for this example? Yeah, good. Okay, let me stop recording first.